Hello, good morning. The topic of my presentation is Colligative Properties from the lesson Dilute Solutions. This is for the B.Sc second year chemistry students. Now, I will be dealing with fundamental concepts. The term colligative was derived from Latin. Colligare means tied or bound together. So, colligare implies the solvent and the solute molecules are tied together or bound together. Now, what are tied together are solute and solvent particles. They are in a solution together bound. These are physical properties exhibited by dilute solutions containing non-volatile solutes. These are physical properties of solutions. Wait a moment, let us deal about them at a later stage. Now, what are solutes? The solutes may be a salt, a sugar, glucose or ethylene glycol. It is used as an antifreeze. Now, volatile solvents have a tendency to vaporize. They go into the space due to entropy. Where there is more entropy, the vapors go into that state, hence the solvent molecules vaporize. Now, when you add a solute which is not volatile, what happens is it obstructs the number of solvent molecules escaping into the volume. Hence, there is a decrease in pressure. These properties are dependent on the ratio of number of solute particles to solvent particles. Now, the ratio may be a mole fraction, it can be a molality, it can be molarity also. The number of moles of solute divided by sum of the particles of solute and solvent, number of moles of solute and solvent will give the mole fraction, whereas molality is the number of moles of solute divided by the weight of solvent in grams further divided by 1000. Now, molarity is also represents the concentration and it gives the number of moles of solute divided by the volume of solution in ml divided by 1000. Now, vapor pressure, boiling point and freezing point are physical properties of solutions. Okay, that is the thing. Now, are these colligative properties in nature? That is what you have to test further. You can see the blue arrow on your screen that shows vapors. Now, these vapors after hitting the lid, they lose the energy and come down and come into the liquid phase. So, after some time an equilibrium is established between the liquid phase and the vapor phase of the solvent. This is called a dynamic equilibrium because it is always in motion. Now, yellow indicator shows the pressure exerted by vapors on the lid. So, this is the vapor pressure that is exerted on the lid of the container. The container is closed with a lid. What is vapor pressure? It is the pressure exerted by the vapors, as already has been told. Now, what is boiling point? Boiling point is the temperature at which pressure equals atmospheric pressure. The vapor pressure equals atmospheric pressure. Now, what is freezing point? It is the temperature at which liquid changes into solid. You can see water getting into the solid form, that is ice. In the next slide, you will know that colligative properties are directly proportional to number of solute particles. Now, how can you know whether vapor pressure, boiling point and freezing point are colligative properties or not? The fundamental basic test is a dependence of a property on number of particles. Now, let us see whether vapor pressure is dependent on pressure or not. It is dependent on pressure and not on number of particles. And also boiling point is also dependent on temperature. Freezing point is also dependent on temperature. So, you can safely conclude that these three physical properties of solutions does not obey colligative properties are directly proportional to number of solute particles. Hence, they do not fall under colligative properties. So, these are not colligative properties. Now, let us know what are colligative properties. These are physical properties, but a special type of physical properties. These are also intensive properties. They depend on the they do not depend on the internal nature, but they depend on physical nature. So, these are relative lowering of vapor pressure, also known as RLVP, elevation in boiling point, depression in freezing point, and osmotic pressure. These 4 physical properties are called colligative properties, and all these 4 depend on the number of solute particles. Let us test whether RLVP, relative lowering of vapor pressure, is a colligative property or not. Let us consider the diagram that was already shown to you. See, you can see the volatile solvent. It is in the vapor state. Solvents have an inherent tendency to escape from liquid phase into vapor phase. Now, when you add a solute, it is obstructing. It blocks the number of volatile solvent molecules escaping into the free space. On addition of a non-volatile solute, there will be an obstruction on the escaping solvent molecule. Now, you can see before and after addition of solute, what is happening? Less number of solvent particles go into vapor phase, thereby decreasing the vapor pressure. You can see graphically the lowering of vapor pressure on adding solute. You can see when you take 1 mole of pure solvent, the vapor pressure of the pure solvent is 23.8 torr. Now, when subsequently on adding the solute, there is a decrease in the vapor pressure, and if you observe at a 0.1 mole fraction of water as solvent, you will see that the vapor pressure will be 2.38, which means the vapor pressure at any mole fraction can be known by the formula P is equal to P naught into x, where x represents a mole fraction and P0 is the vapor pressure of the pure solvent, where P is the vapor pressure of the solution after adding solute, non-volatile solute. Now, here comes the Raoult's law. From the application, when you have seen the graph, there is a consequent decrease on adding the solute molecules. So, the Raoult's law states that the vapor pressure P of a solvent, an addition of non-volatile solute, is the product of vapor pressure P0 of pure solvent and mole fraction of the solute. It has been proved experimentally by showing a graph. Now, considering P is equal to P naught x, since P0 is a constant at a given temperature for a given solvent, hence the equality sin and P naught may be replaced with a proportionality. Now, hence Raoult's law may also be stated as the vapor pressure of solvent containing a non-volatile solute is directly proportional to mole fraction of the solute. This is the other form of the law. Now, let us go to RLVP. When you consider RLVP, there is a lowering of pressure and you relate it to the vapor pressure of the pure solvent. Lowering of vapor pressure of a solvent on addition of a non-volatile solute may be given by delta P is equal to P naught plus P, where P naught is the vapor pressure of the pure solvent and P is the vapor pressure of the solution. Relative lowering of vapor pressure is given by the lowering of vapor pressure divided by the pure solvent vapor pressure. It is a ratio. As already been stated, RLVP adheres to the statement that colligative properties depend on the number of solute particles. Hence, you can safely conclude that RLVP is a colligative property. Relative lowering of vapor pressure, again you can see diagrammatically there is decrease. So, this is P naught and this is P. P naught minus P by P naught, that is the vapor pressure of the pure solvent, will give relative lowering of vapor pressure. Applying Raoult's law to RLVP, the relative lowering of vapor pressure of a solution containing non-volatile solute is equal to mole fraction of the solute. This is the further application of the Raoult's law, where Ns represents the number of moles of the solute, and N0 plus Ns is the total number of moles of both solvent and solute taken together. RLVP is equal to the number of particles and hence is a colligative property. This has been already explained. Ns is the number of moles of solute. How can you experimentally determine relative lowering of vapor pressure? A differential method is used. This uses a manometer. A manometer is a U-shaped tube, and you can see two limbs or two tubes. This is a U tube. It has a left hand side tube and a right hand side tube, and these two are attached to two glass bulbs, A and B. A glass bulb has a solution in it, and B glass bulb has a solvent in it, and the whole thing is managed in a thermostat because temperature variation should not be there. Now there is a stopper or a stopping cork to allow the vacuum pump to take away whatever air is present in it. Now what you do is when the vapor pressure is developed from A, vapor pressure developed will be P, and from B vapor pressure of pure solvent, that is P naught. Maybe so the difference in both these things, I believe this is solvent and this is solution. So this is P naught and this is P naught and this is P. The difference of these things will give the lowering of vapor pressure. When you divide the lowering of vapor pressure with that of the vapor pressure of the pure solvent, it will give RLVP. So this is hence this method is called a differential method because it uses the difference in height levels of the two limbs of the manometer. So this is where difference in heights of both glass tubes of manometer will give delta P. For very dilute solutions, the N naught, which is a number of moles of the solute, will be much less than that of the solvent. It should be lesser. Hence, N naught plus Ns will become Ns. It should be lesser than. It should be lesser than. It should be lesser than. It should be like that. Lesser than. Thank you. Now, application of RLVP. By using RLVP, you can find out the molecular weight of the solute dissolved in the solvent. Here W represents weight of the solute, M is the weight of molecular weight, whereas M is the molarity of the solvent used and W is the weight of the solvent used. So P naught minus P by P naught is equal to W by M into M by W. If you suitably substitute, you get the molecular weight. And there is an experimental method for determining molecular weight of non-volatile solute. This method is called gas saturation method. In this method, you combine several beakers and you arrange them in two series of sets. Each series will have two beakers. The first one has a solution and the second series has solvent. So two beakers containing a solution and two beakers containing solvent, and these are linked with the tubes that will allow the flow of the vapors when dry air is passed at the left hand side end. So you pass the dry air from the left hand side end. Now what happens is when dry air is sent, the vapors are carried away and it is passed into the U tube. This has calcium chloride. It is anhydrous calcium chloride. It absorbs the vapors. Now the experiment is like this. Before anything is passed, the U tube containing the calcium chloride is weighed. Now, after passing the vapors also, it is weighed. Even the beakers are weighed before the experiment is started. Now, what happens is the dry air will carry with it the vapors, along with it the vapors of the solvent from the solution, and also the vapors of the solvent also. Now, what happens is the difference when you weigh it, you will get the weight as the vapor pressure of the pure solvent, and the earlier weighed A beakers, that gives the weight of the solution. So, if you minus the P naught from this weight, you will get lowering of vapor pressure. This is how the experiment is performed. Now, relative lowering of vapor pressure is a very important colligative property that will aid in estimating, determining the molecular weight of an unknown compound. Thank you. Hello. Elevation in boiling point is also a colligative property. Now, we will see how it is going to be a colligative property. Relative lowering of vapor pressure has already been dealt. So, now I would like to deal elevation in boiling point. What is elevation in boiling point and why does it happen? Now, as already been shown to you, boiling point is the temperature at which vapor pressure equals the atmospheric pressure. So, now when you are adding a solute, it decreases the vapor pressure as already been discussed. Now, when you consider the definition of the boiling point, it is the temperature at which vapor pressure equals atmospheric pressure. When you are adding a non-volatile solute, there will be an obstruction on the escaping solvent molecule. Hence, there will be less number of solvent particles going into the vapor phase, thereby decreasing the vapor pressure. Now, atmospheric pressure, when it equals vapor pressure, this is boiling point. It has been already discussed. But you have to consider that this vapor pressure is in dynamic equilibrium with the pure solvent or solution. So, what is happening? Increase in temperature means elevation in boiling point. When you want more number of vapor molecules to go into the gas phase, you need to increase the temperature. So, this increases the boiling point, causing elevation in boiling point. Let us see graphically how boiling point is getting affected. When there is only pure solvent, the vapor pressure will be higher and the temperature required to meet the atmospheric pressure will be less. Now, when there are less number of vapor molecules, the vapor pressure decreases and you need to give more temperature. So, addition of a solute which does not vaporize will increase the boiling point. So, you can see delta Tb. Now, the pure solvent's boiling point is here and the boiling point of this solution is shown here, 1 and 3, 1 and 3, and the difference will give elevation in boiling point. Lowering of vapor pressure and adding solute, elevating boiling point. See, for everything you need an experimental evidence, and here it is a graphical representation of the experiment done. The vapor pressure lowering, you can see it, the vapor pressure is lowering with the increase in the mole fraction of the solute, and there is elevation in boiling point causing increase in boiling point. You can see the right hand side there is delta Tb. Now, elevation in boiling point due to lowering of vapor pressure of a solvent on addition of a non-volatile solute may be given by the formula delta Tb is equal to T minus T0, where T is the boiling point of the solution and T0 is the boiling point of the pure solvent. Applying Raoult's law to elevation in boiling point, the relative lowering of vapor pressure of a solution containing non-volatile solute is equal to mole fraction of the solute. Now, this has been already stated. Now, let us apply this to the boiling point issue also. P0 minus P is equal to P naught into molecular weight of the solvent into W by M into 1 by W. I have brought out the M from this part to the other side, because molecular weight of a solvent is also a constant and P naught is also a constant at a given temperature. Hence, this whole term will become a constant. Hence, this whole term will become a constant. Now, applying Raoult's law to elevation in boiling point, you can see P naught minus P is equal to P naught into molecular weight into W by M into 1 by W. This is a constant. Now, when you consider this equality and these constants, you can replace it with a proportionality. So, P naught minus P is proportional to W by M into 1 by W. So, you also know that delta Tb is equal to P naught minus P. Replacing P naught minus P with delta Tb, that is T minus T naught, you get the final equation. You get the final equation for when the solvent is expressed in grams, solvent weight is expressed in grams, you can divide this with 1000. So, as already been stated, removing proportionality with equality will give a constant called molar elevation constant Kb. So, this proportionality is replaced again with is equal to, and experimentally determined value Kb, molar elevation constant, or ebullioscopic constant is replaced with that. Now, you know that Kb is derived from Clausius-Clapeyron equation, where Kb is equal to R Tb squared by 1000 into Lv. Here R is the ideal gas constant, Tb is the boiling point, 1000 is a constant, and Lv represents latent heat of evaporation, vaporization. It has been experimentally determined. So, the Kb depends on boiling point and the latent heat of vaporization. From the above discussion, it is very clear that these properties are dependent on the ratio of number of solute particles to solvent particles. So, you can see that the boiling point elevation is dependent on molality, which also gives the number of solute particles. It is number of moles of solute divided by weight of solvent in grams divided by 100,000. Delta Tb is dependent on number of particles, as already been discussed. Hence, elevation in boiling point is also a colligative property. Now, what is the experimental method for determining elevation in boiling point? Beckman thermometer has been used. This, as the earlier one, also uses differential method. You can see in the lower bulb, the black indication implies mercury, when it is placed, when the bulb is immersed till here in a till and above the mercury column, mercury bulb, there will be a rise in the capillary, the mercury rises. So, you have to take the solvent and the solution separately and measure the boiling points. The difference in the temperature will give the elevation in boiling point. This is the reservoir that stores the mercury passing through the column. Care should be taken that superheated solutions should not be taken while using Beckmann thermometer. This is Beckmann thermometer. Now, application of elevation in boiling point. You can find out molecular weight of non-volatile solute. There is a method to find out the molecular weight of the solute. It is called Cottrell's method. Here also there is a problem with the Beckmann thermometer, that is you cannot use this with the superheated solutions. Hence, this has been taken care of in Cottrell's method. Here the bulb is a bigger one and it is not as sensitive as the Beckmann thermometer. In Cottrell's method, the Beckmann thermometer is used, but it has been modified. Now, what you do is you take the solution in the test tube like thing, that is the B part of the glass test tube, and you take the solute in the A part of the instrument, and you see that when vapors are released, the thermometer will show the temperature readings of the pure solvent and also of the solution. Now, you can from the difference of T minus T0, you will get the elevation in boiling point. See, there is a condenser to cool superheating. So, this is how Beckmann thermometer has been taken care of. It has been modified for better usage and more precise measurements. This is how you can find out the elevation in boiling point. This is what is the second subtopic, that is elevation in boiling point. Thank you very much. So, now today's my third topic is osmotic pressure. Osmotic pressure is also a physical property. Now, how it is derived? It is derived from the Greek word osmos. Osmos means push. So, the term osmotic pressure means the pressure developed by pushing of the solvent. Osmosis is push or flow process involving solvent. Osmotic pressure, represented by pi, is a pressure developed due to solvent flow. What is the direction of flow? The next question arises is that How does the solvent flow? In which direction the solvent flows? Whenever osmosis occurs, the flow is always from the solution to the solvent. So, flow of solvent from solution of high concentration to low concentration is osmosis. Is it similar to diffusion? What is diffusion? Diffusion is flow of solvent and solute, both solvent and solute flow in opposite directions. It results in homogenization. Hence, whenever a solution is added, whenever a solvent is added with a solute, due to diffusion, homogenization occurs and you get a homogeneous mixture. You know that solution is a homogeneous mixture and diffusion aids in homogenization of the solution. It gives a homogeneous mixture of solution. Is it similar to diffusion? Is osmosis the same as diffusion? No, it is never. In diffusion, both solute and solvent move in opposite directions, whereas in osmosis only solvent moves. And also you can see in the diagram, in the left side diagram, you can see the partition. There is a partition. So, the same vessel has been divided through a partition. This represents osmosis. The left hand side represents osmosis and the right hand side there is a flow of solute and solvent in opposite directions. This depicts diffusion, whereas this depicts osmosis. How does osmosis differ from diffusion? Only solvent flows and partition is required. These are the two things that differentiate osmosis from diffusion. The partition is often a semi-permeable membrane that allows only solvent to flow through it. So, it allows only the solvent to flow through it. Now, what is it? You can see this is a semi-permeable membrane. It is a semi because it does not allow both the solute and the solvent to pass through it. It allows only the solvent to pass through it. Hence, it is semi-permeable. It permits only the solvent. It is a membrane. Now, what is osmosis? You can see an inverted Thesel funnel. Its mouth is inverted and it is covered and the below at its mouth with a semi-permeable membrane, and it is dissolved in it is immersed in water till the mouth ends, and the tube of the Thesel funnel, the neck of the funnel is not immersed. You can see it here, total experimental setup. Now, what happens is because water is in the outer vessel and the Thesel funnel is having having the solution, the solvent has no concentration of the solute, hence it is at a lower concentration, hence the water flows from the outer vessel into the Thesel through the semi-permeable membrane, and due to this there is an increase in the neck level in the tube of the Thesel funnel. So, there is an increase, and this increase will give the osmotic pressure, and this whole process is called osmosis. The flow of solvent from lower concentration to higher concentration through semi-permeable membrane is called osmosis. Here you can see it more clearly. In the left hand side of the U tube there is a pure water, and in the right hand side there is solution. So, whenever I say pure water, you have to consider it as a solvent. Solvent is taken in the left arm of the U tube. Now, it is separated by a semi-permeable membrane. What happens is, in the beginning, initially the solvent flows in both directions, but at equilibrium the solvent, it is not equilibrium actually, the solvent always flows from lower concentration to the higher concentration to the solution side, thereby increasing the height of the solution limb of the U tube. Now, what is semi-permeable membrane? It can be prepared artificially, but naturally some semi-permeable membranes are found. Animal membrane is an example for it, and also cell walls. Cell membrane is also another example of naturally found semi-permeable membranes. Now, some semi-permeable membranes can be made artificially, like cellophane paper and copper ferrocyanide. Now, this is an experimental setup where you will prepare copper ferrocyanide electrochemically. See, the setup is it has a vessel. It has two vessels. It has an inner vessel covered through an outer vessel, and both of them are connected to a battery to allow the flow of electricity. Now, what happens is in the inner vessel you have the copper sulfate. It is taken at a concentration of 0.1 molar, and in the outer vessel you have taken 0.1 molar potassium ferrocyanide. Now, when you pass electricity due to electrolysis, copper tries to leave, Cu plus tries to leave the porous diaphragm. See, this is a porous diaphragm. It has pores. It is not a semi-permeable membrane in the beginning. You are using a porous diaphragm. It is separating both the vessels. Now, when this copper tries to escape, at the same time, due to the flow of electrolysis, due to the flow of electricity, ferrocyanide will try to go into the inner vessel. So, the copper and ferrocyanide will combine to form a precipitate, and the pores are blocked. Now, this porous diaphragm will become the semi-permeable membrane. This is taken out and used for osmosis, for carrying out osmosis. So, this is where it is used. Now, I have already spoken about vapor pressure. It is the pressure exerted by the vapors. Now, what is osmotic pressure in the similar lines? Osmotic pressure is the pulling pressure of a solution, and it is the measure of tendency of a solution to pull solvent into it by osmosis because of the relative concentration of non-penetrating solute and water. So, solute will not penetrate. So, there is a pressure. You call it as chemical potential at higher classes in PG, but now I will say it as the pulling pressure. I will not use the term chemical potential. So, in reality, the difference in chemical potential will make the solvent to flow from the solution of higher concentration to the solution of lower concentration. Now, you can see, as already been shown, this semi-permeable membrane will permit only the solvent to pass in either directions in the beginning, and at equilibrium only one. It is not an equilibrium, but after some time you can say status quo has been attained. There is no further increase, because whatever solvent has to be flown into the solution to see that both the both the sides have similar concentration. Till such a time the solvent flows from pure water or the second side or the left side of the limb to the right side. After that, there will be no further flow. Now, the osmosis has been clearly depicted in this diagram. When glucose is added to pure water, you can see this is solution of glucose, and on the left side there is only water, pure solvent. Now, see, there is a rise in the right side tube. So, this rise from its original position to the newer position is gives the height, and it is directly proportional, or it is equal to the osmotic pressure. This difference in height will give the osmotic pressure. Now, when a pressure equal to this osmotic pressure is applied, then the flow of solvent is arrested. So, this external pressure applied is called hydrostatic pressure. Hydrostatic pressure of a solution is the pressure exerted by a stationary fluidic part of the solution and object. Now, so even when you do not apply an external pressure, a hydrostatic pressure will act in the solution, but this hydrostatic pressure is subtracted from the osmotic pressure, and the net hydrostatic pressure will influence which side of the equilibrium the physical process actually occurs. Now, as water moves by osmosis to side 2, solution on side 2 has two tendencies now. Tendency to push water back to side 1 due to greater hydrostatic pressure, also tendency to pull water by osmosis back to side 2. Now, what happens? So, these to and fro tendencies are there. Now, equilibrium is achieved when tendency to pull water to side 1 and to push water into side 2 balances out. That is how you will achieve the equilibrium, and you can see that this figure indicates the osmotic pressure. At equilibrium, this is the osmotic pressure has won the struggle. Now, osmotic pressure and factors influencing it. Van 't Hoff's equation. Van 't Hoff gave certain laws, just like gas laws. Whenever I speak about gas laws, you remember two important laws. One is Boyle's law and the other one is Charles' law. You know that Boyle's law is it gives the inverse proportionality of volume and pressure. Volume and pressure are inversely related, whereas here you can give the same you can apply the same Boyle's law here and say that pi is proportional to 1 by V. Now, 1 by V gives the concentration. So, pi is in reality directly proportional to concentration. Now, that is Boyle's law. The collective law is called Van 't Hoff Boyle's law. There is one more law, that is Charles' law, in which the volume is directly proportional to temperature. When you combine both Boyle's and Charles' law, you get a Van 't Hoff equation, and if you replace the proportionality constant with a constant R, you get pi is equal to Ct. According to Van 't Hoff's, osmotic pressure depends on the molar concentration of the solution and temperature T, and this is called Van 't Hoff equation. It is pi is equal to Rct or pi is equal to Crt, where R is the solution constant and it is equal to the ideal gas constant. Now, osmotic pressure is dependent on the ratio of number of solute particles to solvent particles. Is it really so? Let us observe. Now, what is molarity? So, you can see pi is equal to Crt. Pi is equal to Crt, where C is concentration. This concentration is expressed in molarity terms. Now, molarity is number of moles of solute divided by volume of solution in milliliters divided by 1000. So, osmotic pressure is also a colligative property. Now, there are certain experimental methods for determining osmotic pressure. Now, Morse has developed a method for estimating or determining the osmotic pressure. Let us see it in a vertical position. This is the actual position. There is a manometer. This U-tubed one, U-tube is a manometer. It measures the pressure. Now, there is a capillary to send the solution. Now, the outer layer, at the outer layer there is a I suppose in the outer layer there is a solution, and in the inner layer there is solvent, and solvent is passed through this layer. It is not clear in the diagram, it needs a larger resolution. Okay. So, when solvent is sent through this top clock, this solvent enters the inner tube or vessel. This is an alloy. This is made up of I suppose brass. Now, these two parts are separated by a semi-permeable membrane. All this is semi-permeable membrane. And now, what is happening is, maybe it is at the lower end. This is a semi-permeable membrane. When solvent is sent, the solvent pushes through the semi-permeable membrane into the solution, and there will be pressure increase. So, this pressure is measured here, and the difference between the earlier pressure and when the solvent is sent will give the osmotic pressure. So, this is how osmotic pressure is measured by using a Morse method. There is an application of osmosis. You can see that pi is equal to CRT. Now, C is concentration, as already been discussed. Now, what is concentration? It is a weight by molecular weight of the solute. Now, you can use molecular weight this formula for determining the molecular weight of the solute that is dissolved in the solution in the solvent to make it a solution. So, osmotic pressure, osmosis is an important thing in determining the molecular weight of the non-volatile solute. Now, how do you identify, how do you determine the molecular weight of an unknown solute? First, you dissolve it in a suitable solvent. Now, you can see the whole setup. This setup is designed by Berkeley and Hartley. Hence, this method is called Berkeley-Hartley method. Here, manometer is not used. You are using a pressure gauge and a pressure meter. There is a Thurzel funnel. It is not inverted as in the earlier case. It is in its actual position. The mouth at the upper end and the tail, that is neck, is attached to a tube. This is called an osmometer. This tube, this whole setup is called an osmometer. This is osmometer, and at both the ends there are corks attached with an opening, and in the left hand side a capillary is attached. So, whenever you send a solvent through this capillary tube, it enters the inner tube, and the inner tube and the outer tube of the osmometer are separated through a semi-permeable membrane. This semi-permeable membrane will allow the solvent, whenever solvent is passed, to pass into the solution, because the solution has a higher solute, hence it flows into the solution, thereby increasing the pressure, and the pressure meter will give the osmotic pressure. This is the high resolution Berkeley and Hartley instrumentation. This is the osmometer. This is the pressure gauge, pressure meter, pressure pump. So, whenever you want to do reverse osmosis, what do you do is you try to give external pressure that is equal to the osmotic pressure, and then the solvent flow is stopped. And if you raise the pressure only infinitesimally, then reverse flow will occur, and this is called reverse osmosis. Now, I'll come to this again. Reverse osmosis, an important application of osmosis. You can see pi is the pressure. Now, you know this. Now, you give pi plus infinitesimally higher pressure, and you can see that the solvent flows in the reverse direction. So, you can purify seawater. You can remove water from saline water, salt water, by applying reverse osmosis. And in Saudi Arabia and several other Gulf countries, this method is most important method for getting water from seawater. So, you can see the sodium and chloride ions being are present in the solution, and they are left alone in the right side part of the tube, and the U tube is separated by a semi-permeable membrane. Solvent flows in the reverse direction, hence it is called reverse osmosis. It is a very important application. So, reverse flow of solvent from solution to solvent by applying external pressure will happen. Now, let us see, let us sum up colligative properties as a whole. Now, you can see that colligative properties actually arise due to the escaping tendency of solvent molecules from the solution phase. It may be vice versa also in the case of osmosis. So, when you consider lowering of vapor pressure, you can see that it is the escaping tendency is proportional to the concentration of the solvent, and it is inversely proportional to the concentration of the solute added. As expressed by, it is expressed by mole fraction, and it is given by Raoult's law. You can see vapor pressure lowering is governed by Raoult's law, and you can see boiling point elevation, that is higher temperature is required to raise escaping tendency to atmospheric pressure, which is 1 atmosphere. So, you can see the whole setup of these physical properties as the escaping tendency of the solvent. You can see the boiling point is expressed by molar boiling point elevation, and freezing point I did not discuss about this today because it is not dealt here, it is not required in this class. Now, osmotic pressure has been dealt, and P needed, osmotic pressure is the pressure needed to reduce escaping tendency of molecules from pure solute into the solution. So, this is how you can deal with this topic. The whole topic revolves around escaping tendency of solvent. This escaping tendency is has been given rise due to entropy, because with increase in entropy the solute tries to escape into the open volume. When you consider elevation in boiling point, you have seen that the vapors are going into the vapor phase. The solvent is going into the vapor phase because of its inherent tendency for rising the entropy. You all know that the natural processes have a tendency where entropy rises. So, escaping tendency is proportional to the entropy, and all these properties are dependent on the increase in the entropy. Thank you very much.
Orbit to ఈ గ్రీన్ ఆర్బిట్ తర్వాత ఉన్న రెడ్ ఆర్బిట్ ఎగ్జైటెడ్ స్టేట్ ఆఫ్ ద ఎలక్ట్రాన్, గ్రీన్ ఆర్బిట్ గ్రౌండ్ స్టేటు. ఎలక్ట్రాన్ అనేది ఈ రెడ్ ఆర్బిట్లో నుంచి అనగా ఎగ్జైటెడ్ స్టేట్లో నుంచి